Welcome to the Deep Dive. Today we're kicking off a brand new series, specifically designed to help you prepare for the CSWIP 3.1 Welding Inspector Exam.
That's right.
Our mission in this deep dive, and actually in the whole series, isn't just about getting the answers right.
No, it's more than that.
It's about really understanding the why behind these critical concepts. Think of it like a focused study session.
Exactly. Sharpening those principles and practices.
Yeah, making sure you're equipped not just for the exam, but, for the real world too. We've got some multiple choice questions lined up.
Good ones.
And we're going to unpack each one, really dig into the insights behind them. Okay, let's jump into the first one. Here's our first question just to get us started. Which type of submerged arc welding, or SAW, is susceptible to breaking down into fine particles during circulation? Your options are A, fused, B, neutral, C, alloyed, or D, agglomerated. Okay, take a moment. All right, the correct answer here is D, agglomerated.
Yeah, and it's really interesting when you look at why. It comes down to how they're made. You see, fused fluxes, they're basically melted like glass granules. Very tough, very robust.
Very solid.
Exactly. But agglomerated fluxes are different. They're made by taking much finer particles and bonding them together, usually with a ceramic binder, then baking them at a lower temperature.
Okay, so more like sticking bits together rather than melting them into one piece.
Precisely. And that structure, while it has its advantages for welding chemistry sometimes, it makes them inherently more fragile, more prone to breaking down mechanically.
Ah, okay.
Think about it during handling, transport, and especially when they're being circulated over and over in the SAW system.
Oh, that movement, yeah.
Right, all that friction, impact, abrasion. It can cause that binder to sort of break down over time. The particles separate.
Leading to those fine particles, the dust.
Exactly. You get an increase in fine dust within the flux system.
That makes sense. The structure dictates the behavior. So, okay, for you listening, if you're an inspector and you know agglomerated flux is being used, what should you be looking out for specifically because of this breakdown issue?
That's a really good practical point. What you really need to pay attention to is the condition of the flux itself as it's being used and reused.
How do you do that?
Well, the key check is the sieve analysis of the recirculated flux. You need to do this regularly.
To measure the fines.
Yes, exactly. It quantifies how much fine powder is building up. If you see a big increase in fines, that's your red flag the flux is breaking down.
And why is that a problem?
Well, too many fines can mess things up. It can affect arc stability, leading to defects like porosity or maybe inclusions.
Right, things an inspector definitely doesn't want to see.
Definitely not. It can also make the slag harder to remove after welding, and in some cases, it might even subtly change the weld chemistry if some of the finer, crucial elements get lost or unevenly distributed.
Okay, so it can compromise the final weld properties.
Potentially, yes. So it's about being proactive, checking that flux condition, not just assuming it's okay.
Got it. A vital check for consistent quality. Okay, let's shift gears now, moving away from flux to non-destructive testing, gamma rays. Here's the question. What determines the penetrating power of gamma rays? Is it A, time, B, type of isotope, C, source to film distance, or D, source strength? Think about that one. What gives gamma rays their punch? All right, the correct answer is B, type of isotope.
Yes, and this really hits on the fundamental physics of it all. It's a super important concept in NDT.
Okay.
See, factors like source strength, how much radioactive stuff you have, or exposure time, they influence the amount of radiation, the intensity.
The more radiation, darker film, that kind of thing.
Exactly. But they don't change the energy of each individual gamma photon being emitted. That's the key.
Ah, okay.
Think of it like light. A stronger flashlight gives more light, but it doesn't change the light's color or its ability to pass through, say, a colored filter.
Right. Makes sense.
It's the specific radioactive isotope, like comparing, say, iridium-192 with cobalt-60, that dictates the inherent energy level of those gamma photons.
And higher energy means?
Higher energy means greater penetrating power. They can travel through thicker or denser materials more effectively.
So it really is about the fundamental energy tied to that specific element, not just how much you use or for how long. Why do people mix this up sometimes? Is it common to think turning up the source strength boosts penetration?
Oh, absolutely. It's a very common misunderstanding. People often confuse quantity with quality,
Right.
They think if they just blast it for longer or use a much stronger source, they'll somehow push through thicker stuff. But physics doesn't quite work like that for penetration.
But what happens if you try?
Well, a longer exposure or a stronger source gives you a darker image. Sure, you get more signal at that energy
Well,
level. But it won't let the gamma rays penetrate material that was just fundamentally too thick or dense for that isotope's energy to begin with.
I see.
You wouldn't use iridium-192 for, say, really thick steel, maybe over 70 or 80 millimeters. Its energy just isn't high enough.
And if you tried?
You'd end up with incredibly long exposure times, which isn't great for safety. And worse, you might completely miss deep flaws that a higher energy source, like cobalt-60, would show you quite easily.
So choosing the right isotope is critical for both efficiency and actually finding what you need to find.
Exactly, matching the energy to the job.
A crucial point.
Oh.
Okay, from gamma rays, let's move to something that ensures structures last. Preventing failure. Next question. To improve resistance to service failure caused by cyclic loading, it is good practice to do what? Your choices.
Yeah.
A, use low heat input welding. B, use steel with a low carbon equivalent value, or CEV. Ensure there are no features that give high stress concentration. Or D, post-weld heat treat, PWHT, the fabrication. What's the best practice here for cyclic loading resistance? Right, the answer is C. Ensure there are no features that give high stress concentration.
Yes, definitely. When you hear cyclic loading, you should immediately think fatigue failure.
Right, the big one.
It's probably one of the most common failure modes out there, especially in structures that see repeated loads. And the absolute key here is that fatigue cracks nearly always start at stress concentrations.
Stress raisers.
Exactly. These can be tiny flaws, or they can be design issues, sharp corners, sudden changes in thickness, weld toes that aren't smooth, even things like rough grinding marks.
Okay.
The problem is, even if the overall stress in the part is low, at these points, the stress gets magnified. Under repeated loading, this leads to tiny cracks forming and then growing.
Until failure.
Until failure. So the most fundamental thing you can do is design and fabricate to eliminate those stress raisers. Smooth transitions, good weld profiles, avoiding sharp notches, that's paramount for fatigue life.
You know, that point about stress concentration is so important. It really drives home that quality isn't just the weld metal, it's the whole picture, design, geometry, finish.
It's a holistic view,
Yeah.
absolutely.
But often when fatigue comes up, people also talk about PWHT, post-weld heat treatment, to relieve stress. Why is avoiding stress concentration generally seen as more fundamental for preventing fatigue initiation than PWHT?
That's a great question because PWHT is important, but for slightly different reasons in this context. PWHT is excellent for reducing residual stresses left over from welding.
Right, the stress is locked into the material.
Exactly. And those residual stresses can influence fatigue life mostly by affecting the mean stress level, which impacts how fast a crack grows once it's started.
Okay, so more about crack growth.
Primarily, yes, but fatigue cracks almost always initiate at a geometric stress concentration. A sharp corner is still a sharp corner, even if the residual stress nearby is low. The applied stress under cyclic load will still get magnified hugely at that point.
So PWHT doesn't remove the starting point for the crack.
Correct. It doesn't eliminate the initiation site. So while PWHT helps, and things like low heat input or low CEV steel improve toughness or reduce cracking risk,
Important things,
but for preventing the start of a fatigue crack under cyclic load, rigorously minimizing those geometric stress concentrations is the #1 priority. It's about preventing the first shot, so to speak.
got it. Build in the resilience from the start in the design and execution. Makes perfect sense. Okay, speaking of execution, let's zoom into a specific welding process now. Gas metal arc welding, GMAW. This question gets right to the heart of controlling it. For GMAW, the burn-off rate of the wire is directly related to what? Is it A, stick-out length, B, wire feed speed, C, arc voltage, or D, travel speed? What controls how fast that wire melts? All right, the answer is B, wire feed speed.
Yes, this is absolutely fundamental to GMAW, especially with constant voltage or CV power sources, which are the most common.
Okay.
The whole system is designed to keep the arc length stable. And the way it does that creates this direct link between wire feed speed and current, which controls the burn-off.
How does that work exactly?
Well, if you turn up the wire feed speed control,
Okay, feeding wire faster.
the system senses the arc getting shorter as the wire pushes in. To maintain that stable arc length it's set for, the power source automatically cranks up the welding current.
More current means more heat at the wire tip.
Exactly. More heat melts the wire faster, increases the burn-off rate to match that higher feed speed and keep the arc length constant.
And the opposite if you slow down the feed speed.
Yep. Slow the wire feed, the power source reduces the current, less heat, slower burn-off rate. It's a beautiful feedback loop.
So wire feed speed is really your main handle for current and deposition rate.
It absolutely is. It's the primary control.
Okay, so that relationship is key. What happens if a welder gets it wrong? And for you as an inspector, what visual cues shout wire feed speed issue?
Oh, the implications are huge. If the wire feed speed is way too high for the voltage setting, the wire literally stubs out into the weld pool.
Jabbing into it.
Yeah, causes a really unstable arc, loads a spatter, and you risk lack of fusion because the arc isn't burning properly. Visually, you might see a narrow, kind of humped up bead, maybe poor wetting at the edges.
Okay, and too low.
Too low, and the arc gets too long. It becomes unstable, might even go out, or you get a very wide, flat bead that likely has insufficient penetration. You might also see undercut along the edges.
So as an inspector, you're looking for?
You're looking for signs of instability. Excessive spatter is a big clue. Inconsistent bead shape, width, or height. A super wide flat bead might mean too low feed speed, not enough current. A narrow ropey bead with lots of spatter could mean too high.
Gotcha. Understanding that link helps you diagnose problems just by looking at the weld. That's powerful.
Incredibly useful on the job.
All right, last question for this deep dive, and it's a bit of a tricky one on defect detection. Lamellar tearing has occurred in a steel fabrication. What technique could have been used to find it before the weld was made? Your options. A, X-ray examination. B, liquid penetrant examination. C, ultrasonic examination. Or D, it could not have been found by any inspection method. Could you spot lamellar tearing before welding? The correct answer here is D. It could not have been found by any inspection method.
Yeah, this one often catches people out because it's about understanding when and why lamellar tearing happens.
Okay.
Lamellar tearing isn't a pre-existing flaw in the steel plate like a lamination might be. It's a defect that happens during or right after welding.
It's caused by the welding itself.
Exactly. It's caused by the shrinkage stresses from the cooling weld metal pulling on the base material in the through thickness direction, what we call the Z direction.
Okay. Pulling perpendicular to the plate surface.
Right. And if the steel has poor ductility in that direction, often because of elongated inclusions or impurities lined up from the rolling process.
It can't stretch, so it tears.
Precisely. It tears internally, usually in steps, parallel to the rolled surface. Since the tear is a result of the welding stresses acting on susceptible material, it simply doesn't exist before you make the weld.
So pre-weld NDT methods like X-ray, LP, UT, they look for existing flaws.
Correct. They can't find a tear that hasn't happened yet.
Okay, so what does this mean for you as an inspector? You can't find the tear beforehand, but you know it's a risk with certain materials or joints. If pre-weld inspection for the tear is out, what are the key preventative things you should be looking for in the WPS or material certs?
That's the crucial shift in thinking from detection to prevention. Since you can't find the tear before it forms, you have to focus on stopping it from forming.
Right.
So first, scrutinize the material specification. Does the steel have guaranteed Z direction properties? That's a big one. It means it's tested for through thickness ductility.
Okay, looking for Z-grade steel sometimes.
Exactly, or simile designations. Also, check the material certs for things like sulfur content. High sulfur makes it much more susceptible.
Got it. Material first. What else?
Second, look at the design. Are the joint details minimizing through thickness stress? Avoid highly restrained joints if possible. Sometimes using buttering layers on the plate surface before making the main weld helps, or using partial penetration welds instead of full penetration where the design allows.
Smart design choices.
And third, the welding procedure specification, the WPS itself. Look for things like low hydrogen consumables. Hydrogen makes tearing worse. Check the specified weld sequence. Is it balanced to minimize restraint buildup? And controlled heat input can also play a role.
So material checks, design review, and careful procedure control.
That's your best defense. Understanding those preventative steps is how an inspector manages the risk of lamellar tearing effectively.
That's incredibly helpful. It really highlights the inspector's role in prevention, not just finding flaws after the fact. Wow, we've certainly covered some crucial areas today, from sauce fluxes and gamma ray physics to fatigue prevention and the specifics of lamellar tearing. Every single one of these questions hits on knowledge that's vital for anyone aiming for that CSWIP 3.1 certification.
Absolutely. And, understanding these concepts deeply isn't just about passing the test.
No, it's more than that.
It's about building that critical thinking, that ability to assess situations and make sound judgments to ensure safety and integrity out there. in the real world. Which actually makes me think of a final question for you listening.
Well,
How does really grasping these individual principles, flux breakdown, isotope energy, stress concentration, defect mechanisms, how does that empower you to make better, more proactive decisions when you face complex, maybe unexpected welding challenges on a real job, not just in an exam scenario?
that's a great question to reflect on. How does this knowledge translate into practical wisdom? Excellent point. Keep that in mind as you continue your studies. Well, thank you for joining us for this session of the Deep Dive. We hope it's been helpful, and we look forward to exploring more essential welding inspection topics with you very soon.